pointed at bits that are connected to JK. And in the graph, which I told you was 3 regular, there are just 3 possible little pictures that could correspond to. One is which the 2 guys connected to J, and the 2 guys connected to K. Let's just do that. One of the guys connected to J, and one of the guys connected to K are themselves connected. What I'm saying, that's what I meant. Or it's just the case that both of the guys connected to J have both guys connected to K, which is like, I have something. So that I just sort of look at a history of the problem, and I can look at I can identify the subunits of it, on which I can actually do the calculation of what I get for the function of gamma and beta. So each subgraph type gives a function usually is very little, and it can be computed doing a little computation which is all and then the function is ratio of 2 p plus 1 over 2 p plus 2 independent of n. So we can show that. And in fact, if p is n over 2, it jumps to 1. As soon as p is big enough that kind of like your subgraphs are seeing the whole graph, this actually jumps to 1. But I want to say another thing about this. You see, at p equals 1, we get a 3/4. And, at p equals 1, we get 3/4 and. Yeah, I left that letter. You know, I used a special font. This is a special Microsoft font that I used, and it failed me there. I'm going to have to write to them. This is an and. Stupid computer. So anyway, at p equals 1, we get 3/4 and for large n. So what I want to say about this is the following thing. If you get an approximation, if I tell you I satisfy the expected value of 3/4, that could be because you have a 75% chance of getting perfection, and every other string is really bad. See, I'm telling you the quantum expected value is 75%. One way I could achieve that is to put an amplitude of the square root of 3/4 on the perfect string, and then put the rest of the amplitude on things which have very bad values. That would also get 0.75. That's not what happens here. What happens here is every string of this output satisfies 3/4 of the bonds. So this is not a failed optimizer trying to achieve perfection. One of the ways, actually, that people sometimes run classical algorithms to look for good solutions is run an algorithm which you know will achieve the best solution if you run it forever, and then terminate early. But this thing doesn't look like it's doing that, because when it terminates, it's producing something that satisfies 3/4 of the bonds, and every string satisfies 3/4. There's nothing in the tail. There's no tail in which the best solution exists. And I think I'm belaboring this point, but I think I want to emphasize here that we're really talking about an approximation algorithm. We're not talking about an algorithm designed to achieve perfection. And I think I want to keep that in mind, because my goals are modest. I don't want perfection. I want good. Okay? So let's keep going. Now let's talk about another problem, max E3 Lin 2. So this is just a little computer science-y, but let's try to bear with me. I'm going to tell you a story. I'm not going to show you any of the details. It's just going to be a story, okay? So this is a different problem. And this problem is max E3 Lin 2. And this is a problem in which I have n variables, and I have m equations. And each equation has 3 variables. So this says there are exactly 3 variables in every equation. Each equation is linear, and it's all mod 2. So for example, each equation is going to be a form. Here's the i's of 0 and 1, sorry. The 0 and 1s. Every equation is in the form zi plus zj plus zk mod 2 is 1 or 0. So what I'm doing, I want you to imagine the following thing. I give you a list of equations. Every equation has 3 variables that sum up mod 2 to either 0 or 1. Now, and I want you to think of m as bigger than n. So, it's easy to specify this. What I do is I give you a list of triples. I say bits 1, 9, and 22 sum to 0. Bits 1, 9, and 75 sum to 1. Bits 22, 39, and 100 sum to 0. I write it down for you. Now, what's interesting about this problem is if you're looking for a solution, you can find the solution by Gaussian elimination. So the decision problem is in P. If you ask me, is there a solution? The answer I can figure that out immediately. So I'm going to ask you a different question. The question I'm going to ask is, if in the unsatisfied case, so I can't solve all the equations, which assignment satisfies the most equations? That's what my goal is. I have a bunch of equations, there are too many equations to satisfy them all, and I want to find the string that satisfies as many as possible. Is that clear? And that's why it's called max E3 Lin 2, because I'm trying to maximize the number of satisfied equations. Is anyone have a question about that already? We're good? But what the problem is, max E3 Lin 2. This is a standard computer science problem. And so the test is to find the maximum NT-hard. And it's NT-hard to find the optimal solution. That means that if you could have an algorithm which is guaranteed to find the optimal solution in all cases, you would then show that people's NP, which solving the Fabry solves the problem. You would be the most famous computer scientist of this century. Or maybe a half the last century. Okay, so this is a very hard problem. Okay? So we're not looking for the best solution, we're looking for a good solution. So now, let's talk about what you might achieve. So let's go back to an algorithm which we might try for this problem, which is guess a random string. So if you guess a random string, we're going to satisfy half the equations. Now comes a really interesting result, which is that if you had an algorithm which you could prove would produce a solution, a string, that had an approximation ratio of a half plus epsilon. In other words, your algorithm outputs a string z, which is guaranteed to satisfy a half plus epsilon. Epsilon, think of epsilon as 10 to the minus 5, or 10 to the minus 20. So a tiny number, but it's of the maximum number that can be satisfied. So you're now just going to, if you guess a random string, you satisfy half. But now you come to me and say, I have an algorithm which for any epsilon, which for some epsilon, a very small number, 10 to the minus 10, will produce an approximation ratio of 0.500000001. Okay, if you could do that, then P equals NP. It's remarkable because it says that even approximating, even finding an approximate solution can be computationally challenging. This is a result of developments in computer science related to something called the PCP theorem. And these are recent results in the last 15, 20 years. They're beautiful results. This was shown in 2001. Okay, so this is a very hard problem because the slight improvement on it is significant. But now what I'm going to do to make improvement is I'm going to give you a little information. I'm going to tell you that every instance of the problem has no variable is in more than d equations. Okay, no variables in more than d equations. So I've told you something. And once I tell you something, you might be able to use that. And in fact, in the year 2000, an algorithm was proposed by a guy named Hofstad in which he could get a half plus constant over d approximation ratio. This does not contradict this, because, you see, if d gets bigger and bigger, it'll fall under any epsilon. So, you know, it's a fixed epsilon. So if I told you I had epsilon 10 to the minus 3, then his algorithm will fail when d is bigger than 10 to the 3. So this is not a contradiction. But anyway, it was an algorithm. So that was the state of it. But then in 2014, we, meaning Goldstone, Guttman, and I, showed that our quantum algorithm could achieve a half plus constant over d to the 3/4. So we beat him. So at that moment, we had a quantum algorithm with a provable exponential speedup for combinatorial optimization over the best known classical algorithm. So we were extremely pleased with ourselves. Because it was, you know, very nice to have that. Now, what happened, though, was Scott Aaronson was also very excited about it. So Scott Aaronson blogged about it. And then 10 computer scientists got together. Oded Regev and Trevisan, they're very capable computer scientists, but it took 10 of them versus 3 of us, and they got an algorithm that achieved a half plus constant over d to the 1/2. Okay, so this was a rapid response to the assault on this problem by a quantum algorithm. You know? So that was kind of annoying, but what do you do? You know? Anyway, but then, I'd like to mention my collaborators, Goldstone and Guttman, but then what we did is we went back to our algorithm and said, well, we were just pleased with ourselves that we had achieved d to the 3/4, so let's look at it more carefully. And it turns out that the algorithm actually achieved a half plus 1 over 101 d to the 1/2 log d. So we were within a log of that. And we haven't been able to improve this, but I don't know whether we just can't improve it or we just got sick of it. I don't know. Maybe it can improve, I don't know. So, anyway, in typical cases, in fact, Ken Glynn was here, says that he worked on this. In typical cases, we could show that if you have random cases, we actually do achieve a half over square root of 3e, d to the 1/2. So, you know, we're very, very close to what's going on with them. But I should say, can we get rid of the...
However, for this video, we want to start off with Vivado to show you the complete flow. Now, we already have Vivado installed and sourced, so we will watch the tool. We will be targeting Vivado 2016.3, which does not include the board files for the VCU 102. However, they are downloadable, and you can set a parameter for the project to enable board automation, and that's what I'm doing here. Now, when we create a project, we'll notice under the Boards tab that the VCU 102 board shows up, and we'll create a project. We'll jump straight into ITI, and give it a name. And then we'll add the PS block to allow us to configure the PS the way we want it to. Now you'll notice, right as I add it, at the top, there's board automation enabled, and this will set it up exactly how it should be set up for the VCU 102. Now there are some things that I'd like to change, and so we're going to go into the PCIe configuration, and we're going to make it 4 lanes instead. Notice that it's set to 1 right now. So here, under the high-speed I/O, you'll notice that there's other I/O in the way, and for that reason, the tool checks and lets you know why. In this case, there was another SerDes being used, the USB 3, and we're not going to be using that, so we'll go ahead and disable it. Okay, perfect. Now we have PCIe as Gen 2 by 4. And then we'll do one last check for the other options. Everything else looks fine. There are, however, some PL interfaces that are not necessary, and for that reason I'll disable them. However, they could be kept there. We'll click OK. We'll save. Check if the validation passes, and it does. Do another save and create the HDL wrapper. We'll let Vivado manage it. And then we'll export the hardware, which prompts us to generate the output files. What this is doing is it's going to create the HDF file that Petalinux will use to determine what to create in the with the device's tree generator. And after this is done generating, we should be done with Vivado. So unlike the Zinc 7000 video, we don't have to wait for a bit stream. We can go straight to Petalinux with this generated HDF. Now we'll close Vivado and work with the Petalinux tools. So I'll go ahead and go into a new directory and create a Petalinux project there, targeting the Zynq UltraScale Plus scale. So I'll give it a name of NVMe test. We'll change directory into there, and then run Petalinux config, and then point to the hardware description file that we exported from the Vado. And now we'll run Petalinux config and modify the root file system. And here we'll want to add several packages to make PCI Express facilities available, and also other facilities to enable us to communicate with the SSD. Now we'll run Petalinux config again, but this time we'll modify the kernel. Here we'll enable the NVMe driver so it can communicate with the NVMe controller. So that's all we need to modify. Now we'll run Petalinux build. That will compile everything and prepare us to package it for an SD card. Petalinux build can take several minutes depending on your system. And after it's done building, we'll go ahead and package. We'll run Petalinux-package. Here we'll need to target the FSDL that was created and built, as well as the ATF, and also U-boot. Now we should have all the files we need to boot from SD. There we'll have the boot.bin, which we'll copy to an SD card. And then also we'll take the image.ub, copy that on the SD card as well. Now we'll take the SD card and plug it into the SD slot. We'll ensure the mode pins are set to boot from SD. We'll insert the NVMe drive into the PCIe slot. Then we'll plug in the UART USB cable, and then apply power and turn it on. Now we're booting and looking at the output from the UART terminal. Our login and password are both going to be root. So I'll type root and root once more. And now we're in. Next I'll run lspci-bdd, and we'll see that the memory controller, the NVMe controller, has a link to the NVMe driver. And this drive has no partitions on it, so we'll add a partition using the fdisk utility. We'll only add one partition, and then choose the defaults for everything else. And there we see the partition it made, and now we'll apply a file system to that partition. It shouldn't take too long. And now we can finally mount the partition to a blank directory and begin using it as a regular drive. We'll go ahead and create a simple file. Now we'll run the df command to see the information on the drive. And then we'll create a file and write to it. Something simple. So save the file, sync it, and then I'll show you the contents to ensure that it's still there. To recap, we created the hardware design in Vivado. We used those settings in Petalinux. We made sure we had the necessary kernel components and root file system utilities enabled. From here, we booted Linux on the VCU102 from an SD card, and then were able to mount the NVMe drive. You too can easily use off-the-shelf PCIe I/O cards to connect to Zynq UltraScale Plus.